Hello, I am Suyash Bhagat, and today I'll be talking about performance trade-offs and design of MimbleWimble proofs of reserves. Before beginning my talk, I'll give a brief outline. First, we'll talk about what exactly is a proof of reserves and why is it necessary. Then we'll discuss Revelio, which is the current state-of-the-art proof of reserves for MimbleWimble. Then we'll discuss RevelioBP, which we have designed, and it's a bulletproofs-based proof of reserves. Then we'll compare the performance of the two, and finally we'll give a couple of directions for future research. So proof of reserves is basically a proof of ownership of certain amount of assets. For cryptocurrency exchanges, the challenge in giving proof of reserves is to do so without revealing any sensitive information. So suppose we have an exchange which wants to prove that it owns certain addresses in the UTXO set, each of which contains some amount. It must do so without revealing what address it owns, and the final proof must look something like this, where the exchange states that it owns some addresses on the blockchain and it contains a total of an amount which is hidden in a Peterson commitment C reserves. The proof must be publicly verifiable, and the commitment is C reserves is a Peterson commitment to the total assets owned by the exchange. On a similar note, a Peterson commitment to the total liabilities also could be computed. Now, if I compute the quantity C reserves times C liability inverse, uh, then as Peterson commitments are homomorphic, this becomes a Peterson commitment to the sum of assets minus the sum of liabilities. If the exchange can prove that this Peterson commitment commits to an integer in range 0 to m for positive m, then the customers can rest assured that the exchange owns at least as much assets as its liabilities, and this all setup is known as proof of solvency. Coming to Revelio, suppose an exchange owns some outputs in the MimbleWimble blockchain, and let's call this set as C own. Each output in MimbleWimble is a Peterson commitment. Let G be a prime ordered group where the order is Q and the generators GH such that the discrete log relation between them is not known. So for an amount A, which is a 64-bit non-negative integer, and a blinding factor K, the output is defined as G power K times H power A. As we already know, Peterson commitments are homomorphic. They are also perfectly hiding and computationally binding. Lastly, the ownership of an output in MimbleWimble implies the knowledge of blinding factor K. So K also acts as a secret key. The first step in construction of Revelio is to first construct a anonymity set where the green outputs are owned by the exchange and the orange outputs are some cover addresses. The exchange must prove that each output in the anonymity set it's either owned by the exchange or it's not owned by the exchange. A Revelio proof looks something like this, where the first n elements are group elements which are tags, and we use these tags to detect collision between multiple exchanges. Then we have C reserves, and then we have these sigma i's, where each sigma I is a non-interactive zero knowledge proof of representation of discrete log. Each sigma I basically proves the knowledge of secret alpha, beta, or gamma, given a statement which has an OR. So the first part in the statement corresponds to the case when the output is owned by the exchange, and second part corresponds to the case when the output is not owned by the exchange. Clearly, we can see that the proof size of Revelio is linear in the anonymity set. Also, the exchanges have a free choice of the anonymity set in the sense that different exchanges giving Revelio proofs can have different anonymity set. So can we have the anonymity set equal to the entire set of unspent outputs? Because larger the anonymity set, better is the privacy for exchanges. But since Revelio scales linearly in the anonymity set size, it's certainly not a scalable strategy. And that's where we design Revelio BP. So the design of Revelio BP is a bit different. First, we define these unit vectors E1, E2 to E5, where we have one in the position where output is owned by the exchange, and we have secret key vector which contains the blinding factor of all the outputs owned by the exchange. The Revelio BP proof looks somewhat similar to Revelio. So here we have first S elements as the tags. Note that in previous case we had N tags, here we have S tags where S is the number of outputs owned by the exchange. Then we have C reserves, and finally we have an inner product proof which proves the knowledge of secret key vector K and matrix E. So matrix E contains E1 to E5 as its rows. And also we have the definition of the output owned by the exchange and the tags which the exchange publishes. Note that the base here GT depends on the block height T. Now note that the term H bar AJ is common in both of these. So we can combine this into a single constraint of this form. And further, we can combine all the constraints for J going from 1 to S with using random scalars. And on simplifying, we have the following equality, where in the base, we have all the publicly known information, while in the secrets, in the exponent, we have all the secrets embedded. From now on, we can use the inner product argument, which proves the knowledge of secret vectors A and B, given a Peterson vector commitment to them and their inner product. So after this step, we use the inner product argument. And since the inner product argument from the Bulletproofs paper gives proof sizes logarithmic in the size of secret vectors, we have the RevelioBP proof size logarithmic in S times N, while the Revelio proof size was linear in N. So now if we plot the proof sizes in kilobytes versus the anonymity set size for a constant S, we see that the Revelio proof sizes, which is shown in blue, and Revelio BP proof sizes shown in yellow. Revelio proof sizes scales linearly, while Revelio BP proof sizes scales logarithmically, and we can see a significant difference in the proof sizes. On the other hand, the Revelio proof sizes do not depend on S, and therefore, for a constant anonymity set size and increasing S, the Revelio proof sizes remain constant, while the Revelio BP proof sizes scale linearly in S. But even in worst case, the Revelio BP proof sizes are at least an order of magnitude smaller than that of Revelio. Now, if we plot running time of Revelio and Revelio BP in minutes for a constant S and increasing anonymity set size. So here the yellow one is Revelio BP generation time, dark yellow is Revelio BP verification, blue is Revelio generation, and dark blue is Revelio verification. So clearly we can see that Revelio BP generation time is at least two times smaller than that of Revelio generation. On the other hand, Revelio BP verification is about 4 times faster than its generation due to single multi-exponentiation check. Here too, if we plot the running time versus S for a constant anonymity set size n, as Revelio is independent of S, the running times remain constant for Revelio, and the running time it scales linearly in S for Revelio BP. So here we had noted that the Revelio BP verification is almost 2 times faster than Revelio verification, and Revelio BP also had an order of magnitude smaller proof sizes. So definitely it seemed to be a better alternative. But the benefit of faster verification is only possible up to a certain S, after which the Revelio BP verification is slower than that of Revelio verification. Lastly, we'll talk about some performance trade-offs in using Revelio BP and Revelio. The proof size of Revelio BP scales as S plus log S times n, while that of Revelio it's order of n. For the current UTXO set of GRIN, which has the size 160,000 and S equal to 50, the proof size of Revelio BP and Revelio is around 3.5 KB and 32 MB respectively. This significant difference in the proof sizes allows for scalability in Revelio BP, and in Revelio BP we set the anonymity set as the UTXO set always. Since the UTXO set is inherently linked to the blockchain state, the Revelio BP proofs are linked to the blockchain state. Revelio BP as well as Revelio both provide output privacy, which means that an adversary cannot figure out which outputs are owned by the exchange. Both are inflation resistant, which means that exchanges cannot inflate their reserves beyond what they actually own. We reveal the own set size in Revelio BP, which might seem to be like a performance drawback of Revelio BP, but it's easy for exchanges to own some cover outputs which contain zero amounts, so as to hide the actual own set size. Running time of Revelio BP is order of s times n, while that of Revelio it's order of n. So for the same parameters, the Revelio generation and verification would take around 34 minutes each, while Revelio BP generation is almost 4 times slower, while verification is almost the same. However, if I change the S to 100, the Revelio times remain unchanged and Revelio BP times are doubled. Since the design of Revelio is quite simple, the Revelio proofs are parallelizable, while since the Revelio BP depends on the recursive inner product protocol, it cannot be parallelized. Finally, since we have recent proving systems like Plonk and Sonic, we can think of using Plonk and Sonic for obtaining constant time verification and constant proof sizes for proofs of reserves. But this will require additional assumptions. And we are already in progress to extend it to cryptocurrencies like Monero. I have added a link to our paper as well as some other references, and thank you.